Welcome back to the third lecture of the fourth week of the course in machine learning. We will continue our discussion about decision tree learning algorithms. We will spend most of the time to talk about the ID3 algorithm. So ID3, which is short for Iterative Dichotomizer 3, is a TDIDT, top-down induction of decision tree algorithm invented by Ross Quinlan in 1986. A TDIDT algorithm returns just one single consistent hypothesis and considers all examples as a batch. This kind of algorithm employs a greedy search algorithm, which means that it performs local optimizations without backtracking through the space of all possible decision trees. Obviously, it's susceptible to the usual risk of hill climbing without backtracking, and as a consequence finds a tree with a short path length, typically, but not necessarily the best tree. This kind of algorithm selects and orders features recursively according to a statistical measure called information gain, which we described earlier in part 1 of this lecture, and until each training example can be classified unambiguously. Some kind of inductive bias is built into this algorithm. On one hand, it's prioritized simplicity, which means it applies Occam's ratio by always choosing the simplest tree structure possible. But also, as already mentioned, it systematically prioritizes for high information gain when selecting features to discriminate among instances. I assume you all know William Mahkum, a monk in the 15th century, started to study logic, and who was the first to phrase the principle of choosing always the simplest solution to any problem. So when there is a choice of alternatives, always choose the simplest variant. This is relevant for the discussion we have now, but as you hopefully already know, is a very useful principle in a number of situations. The ID3 algorithm starts with the original data set associated with a root node. On each iteration of the algorithm, it considers every unused feature and calculates the information gain of that feature. It then selects the feature which has the largest information gain value. The data set is then partitioned by the selected feature to produce subsets of the data that is then associated with the branched out nodes corresponding to the values of the chosen feature. The algorithm continues to recur on each subset, considering only attributes never selected before. Recursion on a subset may stop in one of these cases. Case 1, if every element in the subset belongs to the same class, the node is turned into a leaf node and labeled with a class of these examples. If there are no examples in the subset, it's an empty set, a leaf node is created and labeled with the most common class of the example in the parent nodes set. If there are no more attributes to be selected, but the examples still do not belong to the same class, the node is made a leaf node and labeled with the most common class of the examples in the subset. So throughout the algorithm, the decision tree is constructed with each non-terminal node representing selected feature on which the data is split, and terminals representing the class label best suited for the final subset of this branch. Let us now take a short look at the pseudocode for the ID3 algorithm. I've already informally characterized how the algorithm works, but hopefully by going through the pseudocode shortly, you will consolidate the understanding of how it works. So Actually, this algorithm takes as input a set of instances, a set of classes, and a set of features. And what it does is that it returns a tree, actually. It says return node in the end, but actually a node will, due to the function of the procedure, the algorithm return actually a tree. So it creates the root node in the first iteration, and then it checks if all instances that it has belongs to the same class. So then you have actually a node with maximum purity. Then you return a single node tree with class label belonging with a class label belonging to those instances. If the feature set is empty, there are no more features to choose from in order to split the tree, then you also have to stop the algorithm, and what you return is this single node with a label that is the most common label, class label, still in the set of instances that you have. Otherwise, you still have instances, you still have classes, you still have features, so you select a feature. You select a feature by first calculating the maximum information gain for each feature, and then you select the feature with the highest information gain. And for each value of that feature, you add a new branch belonging to that feature. Then you create a new subset of the instances that satisfies that feature value. If that instance set is empty, then you just create a leaf node with the most common class label you found among those instances. Otherwise, you make a recursive call to the ID3 algorithm again, using the arguments now, the instances, but only those instances to belong to this branch. Of course, you return also have a parameter as the classes, but then you also include the features, but of course you have to remove the feature already used, because according to this algorithm, features are never reused in this process. And finally, the algorithm stops by returning the node. So that's the functionality. Let us now revisit the simple example again that we introduced in part 1 of this lecture. So this was the example where we look at 14 instances, which are characterized by a number of features: outlook, wind, humidity, overcast, and so on. And in this slide, it's depicted how which kind of decision tree is produced by feeding those examples to the ID3 algorithm. So as you see, we had 14 data items to start with, 9 positives, 6 negatives. Obviously, the information gain test decided that outlook was the most relevant feature to use in the first place to discriminate among the instances. And recursively down the way, humidity was chosen. Eventually, wind was chosen. So, and as you can see, given the decision of considering those features in that order, the data set was partitioned so that 5 data items was associated with the outlook sunny case, 4 with the outlook overcast case, rain, 5 items with the rain outlook case, and so on. And as you see, we ended up with actually 5 leaves of this tree. And it turns out that in this case, only 3 of the 4 features were used to produce the decision tree. I will shortly comment on the phenomena of noise. Non-systematic errors in either the values of features or class labels are usually referred to as noise. Typically 2 modifications of the basic algorithm are required if the tree building should be able to operate with a noise-affected training set. The algorithms must be able to work with inadequate features, because noise can cause even the most comprehensive set of features to appear inadequate. And secondly, the algorithm may be able to detect if testing further attributes will not improve the predictive accuracy of the decision tree, but rather result in overfitting. And the algorithm must, as a consequence, be able to take some measures for that, like pruning. Now we turn to the problem of overfitting. So one serious problem for decision trees is the risk of overfitting. It's a significant practical difficulty, and for decision trees and many other predictive models. Overfitting happens when the learning algorithm continues to develop hypotheses that reduce training set error at the cost of an increased test set error. So let's introduce a few definitions. So let's say that the average error for an hypothesis for the training data is called ET. And the corresponding average error for the training data plus the data, in kind of all data altogether, is ED. So we define overfitting in the following way. So if we have an hypothesis, H, we say that this hypothesis is overfitting training data if the ET of H, the ET, which means the training data error for this hypothesis, is less than ET for some other hypothesis, H hyphen. But the ED, the error for test data of H, is larger than the ED for some other hypothesis. So this means actually that there are better other hypotheses with respect to the accuracy for test data. So as you can see in the example to the right, where you can see on the x-axis the size of the tree. So when the tree grows, the accuracy becomes better for the training data, but it's actually more goes down, at least is stable for the test data. So for decision tree, the most important approach to handling overfitting is through pruning. So pruning is the major approach in this case. And the idea with pruning is, of course, reduce the size of the decision tree without reducing predictive accuracy, as measured by a test set or cross-validation set. So there are 2 kinds of pruning. So on one hand, we can have pre-pruning, where you stop to grow the tree earlier, before it perfectly classifies the training data set, which means that no longer data split is statistically significant. So criteria for stopping are usually based on statistical tests, like the chi-square tests. And of course, the aim of this test is to give a ground for decisions whether to expand a particular node or not. The problem with this test, even if those tests exist, is it's still not a trivial problem. So the risk of stopping too early is imminent. The alternative, which is essentially a much more popular approach, is called pruning, which where we allow the tree to grow, so it perfectly classifies the training set, and then afterwards we post-prune the tree by removal of subtrees. I mean, a common approach here is to set aside some part of the data set that we can call a validation set and evaluate and use that validation set as a basis for the decisions in the post-pruning phase. One simple variant of post-pruning is called reduced error pruning. And the scheme for that looks roughly as follows. So actually the data set is split into a training and a validation set. And the validation set is used as a basis for the pruning procedure. All nodes are iteratively considered for pruning. A node is removed if the resulting tree performs no worse than the original on the validation set. Pruning means removing not only the node, but the whole subtree for which the node is the root, making it a leaf and assign the most common class of the associated instances. Pruning continues until further pruning is considered as deteriorating accuracy. So this is a pretty simple procedure, but it pretty well reflects many schemes for post-pruning. Before we leave the top-down induction of decision tree algorithms, I want to say something about some other algorithms. So actually ID3, I would say, is the prototypical algorithm, and therefore I've been using it for exemplification. However, there were much earlier systems of this kind, one of those called CLS. And actually ID3 is an extension of CLS. Also Quinlan, who developed ID3, followed up this work, and there are actually more current versions that are in practical use. That's called C4.5, and there is also something called C.5. And actually C4.5 was at the time considered the default machine learning algorithm. That means a very popular tool to use for machine learning. And then there are others, ACLS, Assistant Cart, etc. So there are many alternatives. In general, one can say that the later system extends ID3 in various ways, but the primary ways are actually that it extends the kind of data types that are allowed for the features, because ID3 was pretty restrictive here. Also, the later algorithms are much better with respect to pruning, and they're also much better with respect to noise handling. So to further emphasize what I said for the last slide, you can see on this slide how a subset of these systems are compared. So let's just look at ID3 and C4.5, and then you can see that on the points where C4.5 is working a better performance than ID3, because it can handle more a wider range of feature values. It can handle missing values, which more or less is equivalent that it can also handle noise, and obviously it has a more sophisticated pruning techniques. Still, there are things that are not handled in C5.5, like also handling the case of outliers, which is also a common phenomenon. But as you can see, another system like CART has mechanisms for handling that. So far we have talked primarily about approaches to building decision trees, which have the purpose to build one single tree. As you remember, most of these methods performs in a greedy fashion, which means that they take local decisions to form the tree, and therefore cannot be guaranteed to result in an optimal, a globally optimal tree. So there is another category of approaches called ensemble approaches, or ensemble methods, which construct more than one decision tree and use the set of trees for joint classification. So there are two kinds of approaches relevant, which are not only relevant for decision trees, but for different kinds of classifiers. So we have boosting approaches, where boosting means that we take a sequential approach, where a sequence of average performing classifiers, it can be one decision tree, second decision tree, third decision, can give a boosted performance by feeding experience from one classifier to the next. So we use experience from the first to improve the performance of the second. One example of such a system is called AdaBoost, which is not only applicable to decision trees, but to many ML algorithms. The other variant is called bagging approaches, where bagging is a parallel approach, where a set of classifiers together can produce partial results fully in parallel, that then can be used to form the basis for a total negotiated result. So one example of that is called random forest algorithm, which combines random decision trees with bagging methodology to achieve very high classification accuracy. So to take a concrete example of an ensemble method, we can look at random forests or random decision forests, which are techniques can be used for classification, regression, and other tasks. So random forest operates by constructing a multitude of decision trees at training time and outputs the class that is the most common of the classes, or mean prediction produced as results from the individual trees. The random forest approach is also an alternative remedy for the decision tree problems of overfitting. As you can see to the left, you can see illustrated how the outcome of the individual trees are used as a basis for some kind of majority voting to decide upon a final class or a final regression value. And to the right, you can also see illustrated that in many cases the accuracy becomes better. So when using the random forest approach, you can get a much more smoother result that is closer to the desired output. So this was the end of lecture 4.3. Thanks for your attention. The next lecture, 4.4, will be on the topic of instance-based learning. Thank you and goodbye.